All right, so you mentioned thermal energy and bond energy. Let's start by taking a look at those. So first of all, what has to be happening in order for each one of these to be involved? Like, how would you know that thermal energy is changing?
If the temperature is increasing or decreasing?
Yeah, thermal energy is all about temperature changes. Versus bond energy is associated with what other type of change?
Change in mass.
A change in mass. Specifically, I mean, we got to be a little more specific about that, because as an object goes through these changes, it's not like its total mass is changing, but what is changing about its mass?
Change of mass and the phase change.
Right, change in how much of that mass is in each phase, like how much of it is solid, how much of it is liquid, how much is gas. So it's associated with some or all the mass changing phase, whether it's solid, liquid, gas, whatever. And we also kind of consider chemical reactions to be a form of bond energy change as well. I usually think of the physical bond energy and the chemical bond energy as two different things. Are you changing the phase, or are you changing what type of molecules are involved? But they all involve changing bonds. So we sometimes lump chemical reactions into bond energy also. But for now, we're just going to be looking at it in terms of phase change: melting, solidifying, vaporizing, condensing, stuff like that. And for each one of these, have you seen the idea of an indicator variable yet? Or what do we mean by an indicator variable?
So like, let's say it's like going from solid to liquid, the mass of the liquid would increase. So that would be an indicator, because solid has less bond energy and liquid has more bond energy.
Exactly. For bond energy, we want to treat mass as the indicator, and specifically mass of that higher energy state. So if you're comparing solid and liquid, you use mass of the liquid. If you're comparing liquid and gas, you'd use gas, because that's the higher energy state or higher energy phase. So the indicator for bond energy is the mass of the higher energy phase. And then for thermal energy, it's a bit simpler. It's just the temperature. And when we say indicator variable, we basically just mean a quantity you can measure that tells you that this type of energy is changing. You can't really directly measure energy. You can't just attach an energyometer to an object to figure out how much energy it has. But you can measure a temperature of the object with a thermometer and use that to figure out how much thermal energy it has, or how much the thermal energy is changing. You can't directly measure bond energy, but you can definitely measure mass with balance scales. Figure out how much mass is in each phase and how that changes, and then use a formula to convert that to how much bond energy it has gained or lost. And we should expect these to be proportional. If you're talking about thermal energy, or at least change in thermal energy, because we generally don't care how much energy it has. We care about how much energy is changing, how much it's gaining or losing. The change in thermal energy should be proportional to the change in temperature. The change in bond energy should be proportional to the change in mass in some phase. Have you seen this proportionality symbol before? Let's take a closer look at that. If we have this idea of proportionality, if we're saying that let's say we have two variables, x and y, and we're saying that y is proportional to X. What do we mean when we claim that Y is proportional to X? What are we saying there?
That if there is a change in Y, it'll be represented in X and vice versa.
Yeah, each one is changing, and specifically changing in the same sort of way. And specifically, we're talking about changing in terms of ratio, of multiplier. For instance, if you multiply X by 3, the value of Y also gets multiplied by 3. If you divide X by 5, then the value of Y also gets divided by 5. A direct proportionality means these are changing with the same multiplier or changing with the same divisor. So that's one meaning of proportionality. But it also means if it's proportional in the sense of changing in the same way, you can also rewrite that as an equation. If Y is proportional to X, we can also say that Y equals what? If you know two quantities are proportional, what equation should you be able to set up? Can we just say that? What was that?
Y equal K times X?
Yeah, Y equals some constant, K or whatever you want to call it, times X. We're not saying that Y and X are equal to each other. If they were, we'd just say Y equals X instead of Y is proportional to X. But if we know they're proportional, then they have to be one of them equal to the other times some constant. And the exact meaning of that constant depends on the situation, what variable we use, what units of measurement it is. But proportionality always means you can set up an equation like this, that one of the variables equals something times the other variable. So let's try that with these two situations. If we're assuming that change in bond energy is proportional to change in mass, that is, changing more mass requires more energy transfer. For example, let's say you melt 1 kilogram of ice and you measure that it takes a certain amount of heat. If you want to melt 5 kilograms of ice, it should take 5 times that much heat because you're changing 5 times as much. So we should be able to rewrite this proportionality as an equation. Delta E bond better equal delta mass times something, some constant. There's got to be some constant we can multiply by the amount of mass we want to melt to figure out how much energy it's going to take to melt it. And what do we call that constant?
Delta H?
Yeah, it's usually written as delta H. And exactly what that is called varies from textbook to textbook and from class to class. I've also seen it as delta M times L, L standing for latent heat in the sense that it's sort of thought of as a heat that is hidden inside the object. So various different ways of writing it. But in this class, we're going to be calling it delta H. That is often read as the heat of melting or heat of vaporization if we're talking about a change between liquid and gas. So heat of melting and heat of vaporization mean the same kind of idea, just two different transitions. Transition between solid and liquid in either direction, and transition between liquid and gas in either direction. And that's just a property of the material itself. And to look at that heat of melting in more detail, there are a couple of things that are useful, a couple of algebraic techniques that are very useful to get more information about some constant proportionality. We just defined a new variable, a new value, by setting up this equation. Algebraically, what do you think we could do to get more information about what delta H really means? Usually in algebra, what do you do if you want to find out more information about a variable?
You isolate it?
Yeah, so let's try isolating this. If you isolate delta H, the heat of vaporization or heat of melting, what would you get here? How would you isolate delta H here?
Delta E. You would get delta E bond over delta mass.
Delta E bond over delta mass. In other words, we could think of the latent heat, or the heat of melting or heat of vaporization, or whatever you want to call it. We could think of that as a ratio, or rate of change. This variable, this value represents the rate of change of how much energy it takes per kilogram of mass that you're changing. And it's very useful to think of ratios like these as unit rates. If you imagine the denominator being, well, what's the easiest number to divide by? If you could divide by any number, what would be the easiest number to divide by?
1.
So let's try just pretending the denominator is 1. If you imagine the denominator is 1, delta energy divided by 1 is just itself. So delta H could be thought of as meaning the amount of energy it takes to melt or boil exactly 1 kilogram of that substance. So delta H for water melting, or ice melting, for instance. Delta H for ice melting is the amount of energy it would take to melt exactly 1 kilogram of water. Delta H for oil boiling is the amount of energy it would take to vaporize exactly 1 kilogram of oil. It's a unit rate. It's the amount of energy it takes standardized to exactly 1 unit, 1 kilogram. Any questions on that so far? And as for units there, if we take a look at the units of measurement, what's the units of measurement for energy? We usually measure energy in what?
In joules.
Joules, yeah. So this is measured in joules, capital J. And then mass would be measured in
Grams, kilograms.
Yeah. And we could use either, but we're usually going to use kilograms just for standardization. So that means the unit for delta H is joules per kilogram. Or since we're often using rather large numbers here, it usually takes a lot of energy to change a phase. We often write it as kilojoules per kilogram. How many kilojoules it would take to vaporize 1 kilogram of the substance. Any questions on that? If system C has same mass as A, but has heat capacity per unit mass, what do you mean the proportion of C to A? Proportion of what in those systems?
Oh, the final temperature.
The final temperatures?
Yeah.
Do we know anything about what's happening to them?
Nope. Or you're adding the same amount of thermal energy, but other than that, you don't know.
Well, let's take a look at thermal energy, because we've got the bond energy formula. We can use this idea to build a similar formula for thermal energy. Any questions on the bond energy formula so far? So if you want to know how much energy it takes to melt or boil something, you just look at how much mass you want to change, usually written as final amount minus initial amount in that phase, higher energy phase. And then delta H, you can usually look up on a data table for that substance. One other way you can write that, by the way, what's another way you could describe how much of a substance there is other than just its mass? You could describe the mass of the object, or you could describe
the moles?
Yeah. In chemistry or when dealing with gases, we usually describe it in terms of how many moles. So we could instead say delta E bond is change in number of moles, usually written as lowercase n, times delta H, the molar heat of vaporization, delta H mole. So this would be number of moles that are changing phase, times, and then this would be the energy per mole instead of energy per kilogram. So for this reason, delta H, like a table of values that tells you delta H, for example, right here we've got a table of values listing, where was it? Heat of melting, if you can see that. This column for heat of melting has 2 different values for everything. One in kilojoules per kilogram, one in joules per mole, or kilojoules per mole. So you want to use whichever one of those values have the units of measurement that matches. If your measurement is in moles, use kilojoules per mole. If your measurement's in kilograms, use kilojoules per kilogram. You want everything to match up. Any questions on bond energy so far? So let's take a look at the thermal energy. Again, we have a proportionality. So we should expect that this thing, change in thermal energy, should equal some constant times this thing, change in temperature. Just like with any proportionality. And what do we usually call this constant here? Have you seen a formula for that yet? Yeah, that's typically called C, the heat capacity. And for this one here, we're usually going to use a capital C, called the heat capacity. And again, we could get more information about that by solving for it algebraically. Heat capacity, if you isolate that, what would you get? How would you isolate capital C here?
Divide by delta T.
What was that?
Divide by delta T on both sides.
Yeah, divide both sides by that change in temperature, you get change in energy over a change in temperature. So just like the delta H, the heat of melting, was the ratio of energy per unit of mass change, the heat capacity of an object is the ratio of change in energy per unit of temperature change. Again, it's useful to visualize the denominator as exactly 1. So you could think of the heat capacity as the amount of energy it would take, the amount of heat you'd have to add to make the temperature increase by exactly 1 degree Celsius or 1 Kelvin. So that's it. That, once again, it's a unit rate, a rate of change. Heat capacity of an object is energy required per degree of temperature change or per Kelvin of temperature change.
I have a question.
Yeah.
So with capital C, so capital C is the heat capacity and lowercase c is the specific heat. So would capital C equal mass times specific heat, lowercase c?
Yes, because the heat capacity depends on the size of the object. If you're talking about, like, let's say you've got 2 objects and you're adding the same amount of heat to both of them, they're not necessarily going to change temperature by the same amount. One of them might be.
Yeah.
So the heat.
So heat capacity. I was just going to say, so heat capacity is mass dependent and specific heat is substance dependent.
Exactly. Heat capacity, since it's the energy per temperature change, a large object is going to take more energy to change the temperature than a small object would. So heat capacity is a property of the object, including how big it is. Heat capacity of the object. But since heat capacity depends on how big the object is, that is the mass, we can expect that heat capacity is going to be mass times something. And that something is what we call the specific heat, lowercase c. So we've got the heat capacity of the whole object, which includes how big it is. But that's equal to the mass of the object times another property called specific heat, which is actually, it was originally called the mass specific heat capacity, because it's the heat capacity specific to the mass of the object, or standardized to the mass. In the same way that delta H is kind of energy standardized to 1 kilogram, the mass specific heat capacity, or specific heat, is the heat capacity scaled to exactly 1 kilogram. Because if you plug in exactly 1 kilogram for M, C times 1 is just itself. So you could think of the specific heat, again, it was originally mass specific heat capacity, but these days we generally just call it specific heat. The specific heat is the heat capacity of exactly 1 kilogram. And again, you can see that by solving for little c. You get capital C divided by mass. So once again, you could think of it as a ratio. The specific heat is the heat capacity per kilogram. Or alternatively, you could write it as a molar specific heat is the heat capacity per mole. Heat capacity of the object divided by number of moles. And the nice thing is this standardizes it. If you've got half a dozen different pieces of, let's say, iron, all these different pieces of iron have different heat capacities because they're different sizes. But for each one of those pieces of iron, if you take its heat capacity divided by its mass, you get the same ratio. So you'd have the heat capacity of a 5 kilogram block of iron and the heat capacity of a 3 kilogram block of iron, and the heat capacity of a 10 kilogram block of iron will all be different. But if you calculate specific heat, it's just the specific heat of iron. And the nice thing about this is you can then look that up on a data table. You can have a data table of specific heat of solid iron, specific heat of solid ice, specific heat of liquid water, specific heat of solid copper, specific heat of nitrogen gas, and so on. So specific heat is very predictable and standardized because it's for exactly 1 kilogram. Or if you're talking about molar heat, it's for exactly 1 mole. Any questions on that so far? So let's put all this back together into one big formula. So we've got delta E thermal equals heat capacity of the object times delta temperature. Or we can replace heat capacity with mass times specific heat. Little c. And if you know the mass of the object, which you could measure with a scale, and you know the specific heat, which you could look up on a data table for that substance, and you know the change in temperature, then you can calculate exactly how much energy that change would take. Or alternatively, instead of writing it in terms of mass, you could write it in terms of number of moles. Heat capacity could be rewritten as number of moles times molar specific heat times change in temperature. Same idea, just a different way of describing how much of the substance you're dealing with. So any of these formulas is valid for thermal energy. You just want to use whichever one matches most closely the information you have and the information you're trying to find. Any questions on that so far?
Yes, could you please explain when to use like moles or like kilograms? Like I know that moles is like during chemical like reactions, but like I'm unsure.
It largely just depends on what information is provided or what information you already have. So regardless of the situation, whether you're talking about putting a hot block of iron into cold water, or whether you're doing a chemical reaction or anything, whatever you're dealing with, it could be measured in kilograms or it could be measured in moles. They're just two different ways of describing how much of the substance there is. So which formula you want to use really just depends on what information you have. If the object's size is described in kilograms, you'd use the one with mass. If the object's size is described in terms of number of moles, you use the one with number of moles. And likewise, you'd want to look up the corresponding value with those units in the data table you've got.
That helps, thank you.
Any other questions on that so far? And let's also take a quick look at the units of measurement for this as well. Temperature is going to be measured in what units? What are our usual units of measurement for temperature?
Degrees.
Kelvin or Celsius?
Kelvins or degrees Celsius. And when we're writing out the formulas, we're typically going to write it as kelvins. Although Kelvin and Celsius are basically the same scale, just shifted to a different 0 point. A change of temperature of 1 degree Celsius is the same as a change of temperature of 1 Kelvin. Like going from 30 degrees Celsius to 31 degrees Celsius, or going from 300 Kelvin to 301 Kelvin, plus 1 Kelvin and plus 1 degree Celsius are the same change. The only difference is what temperature we're calling 0. Then energy, as before, is measured in joules, or let's say kilojoules. So in order for this to balance out, what does heat capacity have to be measured in? What's the only thing that could go here that would make
Kilojoules per Kelvin. Kilojoules per Kelvin.
Exactly. Kilojoules per Kelvin, because that'll cancel out kelvins and introduce kilojoules. So the heat capacity is going to be measured in kilojoules per Kelvin, which you can think of as how much energy it takes to change the temperature by 1 Kelvin. If we then split that up, we're splitting out a kilograms, so we're going to have a kilograms in the denominator as well. Specific heat is going to be measured in kilojoules per kilogram Kelvin, because we need to cancel out the kilograms from the mass also. Versus molar specific heat is going to be kilojoules per Kelvin mole, because we need to cancel out the moles as well. And that's often listed as joules per Kelvin mole just by tradition. So keep track of whether it's joules or kilojoules. I would recommend writing out the units whenever possible, just to make sure you're keeping track of what everything's measured in and make sure they all match up. Any other questions on those formulas so far? So let's try putting these together into an example. Let's say we have a block of ice. Let's say 3 kilograms of ice is currently at -10 degrees Celsius. And let's say we want to completely melt this. So in order to do that, we want to figure out how much heat is going to be needed. Because in order to melt this, you've got to add heat. And we want to figure out how much heat we have to add to make this happen. Any thoughts on how we might be able to organize the information here in a useful way?
We could use an energy interaction diagram.
Yeah, an energy interaction diagram would be really useful for figuring out how the different types of energy interplay here. But to do that, we're going to need to know what types of energy are changing. And sometimes it's pretty easy to figure that out just by looking at the situation. Sometimes it's a better idea to draw out another model to figure out what types of energy are changing. What's another model that's going to be really useful for looking at what types of energy are changing and how?
The three-phase diagram.
Yeah, let's take a look at that three-phase diagram as well. In fact, I would usually recommend starting with that in cases like this. Anytime you're dealing with changes in temperature and or phase, it's often a good idea to draw out, or at least imagine, a three-phase graph, graphing energy added versus temperature, to get an idea of what changes are happening. So if we take a look at our usual three-phase graph, and why is it shaped like this? Why does it go up diagonally for a while and then go flat for a while? What's the difference between those?
Those indicate transition states.
Yeah, these are different states, right? If it starts off really cold and really low energy, it's presumably in what state?
Solid.
Yeah, so this represents solid. It's diagonal and positive slope because if you add energy, you raise the temperature. Add more energy, you raise the temperature more. Add more energy, you raise the temperature until you get to a certain transition point, which for water is what temperature?
0 degrees Celsius.
Yeah, 0 degrees Celsius, or 273 Kelvin, whichever one makes the most sense under the circumstances. After that point, you add more energy, and what happens?
The temperature stays the same and you get a solid liquid mixture.
Yeah, temperature is staying the same, which is why the graph is flat. You're just adding energy, but you're not changing the temperature at all. Instead, the energy you're adding goes into changing the phase. You're breaking bonds, allowing particles to move more freely, transitioning from all solid to part solid, part liquid to all liquid. Once it's all liquid, then you add energy and it continues raising its temperature again until you get to another important transition, the boiling point, which for water would be
100 degrees Celsius.
Yeah. Nice, neat, round numbers, because that's what the Celsius scale was invented for in the first place. Add more energy, and you're not changing the temperature, you're just breaking bonds even more to change from liquid to partly gas, partly liquid to all gas. If you continue adding energy past that, you're just making the gas get hotter and hotter, but it doesn't go through further phase changes. So this would be a complete three-phase diagram, but of course we don't need the whole thing here, because what temperature are we starting at?
-10 degrees Celsius.
Yeah, this block of ice starts off solid at -10, so that's going to be somewhere around here as our initial state. And where do we want to end up?
The farthest corner in the solid dash liquid.
Yeah, because we want to warm it up. In order to melt it, we need to warm it up first, and then add even more energy to make it melt. But as soon as it gets to this corner, it's now all liquid, so we're done. We don't need to add more heat beyond that. If it had said we want to melt it and warm it up to 20 degrees or something, we need to keep going. But if it's just melt it all, we've done that. We can stop there. And the thing is, we don't really need the rest of this graph here because it's not going to hotter than 0. It's not going to melt, or it's not going to boil, I mean. So what's often useful here is to draw a more zoomed in version of this graph. Instead of the whole graph, because we don't really need all this stuff up here, let's focus on a more zoomed in version of this. Let's look at just the temperatures ranging from, let's say, from -10 to 0. We know the graph is going to look like this. We know we're going to start here at -10, warm up until we get to 0, and then melt until we get to all liquid. How many different processes are really happening here? Or how many different types of energy are changing?
2 types.
Yeah, 2 types of energy. Because if we take a look at from the initial situation to this corner, and then from this corner to this corner, this transition is a change in what type of energy?
Thermal.
Thermal energy.
Yeah, since we're changing temperature, this represents a delta E thermal. And then from this one to this one, we're instead changing phase. So that represents what?
Changing bond energy.
Right, that's our delta E bond. So the total change in energy comes from the thermal energy change plus the bond energy change. Any questions on that so far? One other important thing about this graph I'd like to point out before we move on to the energy interaction model. Anytime you've got a straight line on a graph, or even if it's a curve, you could draw in a tangent line. What's the most important single property of a straight line mathematically? If you could just give me one number that tells me almost everything I need to know about a line, what would that one number represent?
Slope.
Yeah, the slope. Slope is probably the most important single attribute of a line. If you know the slope, you know almost everything there is to know about a line. If you also know one point that it goes through, you know everything else too. So if we take a look at the slope of this line, rise over run, and this is often a very good idea. Anytime you're dealing with some new quantity that represents a line on a graph, it's often a very good idea to ask yourself, what does the slope of this actually mean? Does the slope of this have some physical significance? Like for this one, rise over run, the rise here is a change in what variable? What does this axis represent?
Temperature.
Yeah, temperature. The rise here is a change in temperature. And it's very commonplace to try to think of this as the y-axis. That's generally how we learned it in the first place. But keep in mind, this axis does not represent some hypothetical abstract variable y. This axis is the temperature axis. So try to get used to thinking of graphs like this, not in terms of an x-axis and a y-axis, but in terms of what they actually mean. In this case, an energy axis and a temperature axis. The rise on this graph is a change in temperature, and the run is a change in
Energy added.
Yeah, a change in how much energy you're adding. So that means the slope of this graph, rise over run, would be change in temperature divided by change in energy. The ratio of temperature change over energy change. What does that look very similar to? What other ratio were we just looking at that has almost exactly the same structure?
The delta E thermal reaction had something similar.
Sorry, which one?
We were going over the E thermal reaction, and that was kind of similar.
Yeah, we were defining delta E thermal with the formula heat capacity times change in temperature, which meant when we solved for heat capacity, what did we get?
We got change in temperature over change in energy, thermal energy.
Almost. In this case, though.
Oh, sorry. It would be change in thermal energy divided by change in temp.
Yeah, exactly.
Sorry about that.
No worries. It's the same thing, just upside down. So heat capacity is change in thermal energy over change in temperature. That's exactly the inverse of the slope on this graph. The slope of the energy versus temperature graph is 1 over the heat capacity. So this is what I mean by saying that sometimes the slope has an actual physical meaning. It's a very good idea when you're dealing with graphs to write out the slope in terms of what's changing this way over what's changing this way, and ask yourself, does that ratio mean something physically? Does this look like some ratio we've already defined as some important constant? Because often it does. Sometimes it doesn't. Sometimes it doesn't really have much physical meaning. But in many, many cases, that ratio, that rate of change is something with a name, is something with a physical significance. So keep a watch for that. And it makes it very easy to see, like just looking at the graph, if you say, well, this line's really steep and this line's less steep, that immediately tells you something about the heat capacity of that substance. Any questions on that so far? So let's try, now that we know what types of energy are changing, which is one of the main ideas to get from a temperature versus energy graph, let's see if we can turn that into a three-phase or an energy interaction graph diagram. So we know that there is a thermal energy increasing. And physically, what's changing that tells us the thermal energy is increasing? What's the indicator variable there?
The temperature.
Yeah, temperature is increasing, which is what tells us that the thermal energy is increasing. So in 7a, we're typically going to write that like this. The type of energy that's changing, and then an arrow telling you whether it's increasing or decreasing. Then in parentheses under that, the indicator variable that tells you that information, that tells you why it's changing. And we can even write out initial and final values. What temperature does this ice start at?
Negative 10 degrees Celsius.
Yeah, starts at negative 10 degrees Celsius, and we're assuming it ends at what?
0 degrees Celsius.
Right, 0 degrees Celsius. Even if we had the water continue to warm up afterwards, we'd end this situation at 0, because once it hits 0, it's not going to be ice anymore. So we've got a change in thermal energy. We've also got a change in bond energy. And would you say the bond energy is increasing or decreasing? Do you have to add or remove energy to make it melt?
Increasing.
Yeah. Increase in bond energy corresponding to bonds breaking. We're making the molecules more free to move by turning it into a liquid. For the indicator here, we want to use mass, but specifically which mass? Mass of solid or mass of liquid?
Mass of liquid.
Yeah, because that's the higher energy phase. And the mass of liquid, if we take a look at these starting and ending values, how much liquid did we start with?
0.
0.
In the situation, we had no liquid at all. It was all solid. So we started with 0 kilograms of liquid. And assuming it all melts, how much liquid do we end with?
100% liquid.
It is 100%, but I think it would be more useful to write it as an actual numerical value of mass. How much mass? How many kilograms of liquid do we have at the end?
3.
Yes, we end with 3 kilograms of liquid. And it's useful to write these as actual numbers of kilograms or number of moles if you can, because then you can actually subtract them and use that in your calculations. And we can now see that we're going from a small amount of liquid, none at all, to a large amount of liquid, 3 kilograms. So we're increasing the amount of liquid, the amount of the higher energy state, which corresponds to the idea that the bond energy is increasing as well. So it's nice if we can set up the system, set up the model in such a way that these changes match up. I think that's all that's changing in terms of types of energy. The ice is warming up and melting, and that's the only thing that's changing. Now the big question is, should we treat this as an open system or a closed system?
An open system.
Yeah, this definitely looks like an open system. And how can we tell? What is it about this that suggests this is an open system?
Because there's no other object making the ice melt.
There's nothing else involved, right? We've got an increase. If this was a closed system, what would you expect the changes to add up to if it was a closed system?
0.
Right. In a closed system, the changes have to add up to 0. Closed system, the change in E total must be 0. Because the things in the system would be only interacting with each other, nothing else involved. In this case, though, we've got an increase plus an increase. There's no way you can have an increase plus an increase add up to 0. You've got to have something decreasing to balance it out. Since we don't have that, this is not a closed system. It's got to be an open system. And we can also see that more conceptually. In order to melt this ice, what do you have to do to it?
Add energy to it.
Right, you've got to add energy, and that energy is coming from somewhere else, somewhere outside the system. Maybe you're putting it on a stove and turning on the stove. That means you're adding extra energy, presumably chemical energy from the burning of gas, or maybe electrical energy coming from a power plant somewhere else. But that's energy coming in from outside the system we're considering. Now, if you expanded your system, if you included in the system the chemical energy of the gas you're burning, then that could be a closed system. But we don't want to include that here. We just want to say there's heat coming from somewhere, we don't know where. So we're going to treat this as an open system, usually represented by drawing a box around this with dotted lines. And we're adding energy in the form of heat. So we're going to say heat is entering the system, which we're generally going to represent by an arrow pointing inwards, labeled Q. We usually use Q to represent heat. I'm not entirely sure why. I think it probably stands for a thermal quantity or something like that. Or it might stand for something in French or German, I forget. But in the case of an open system, instead of delta U total equals 0, we'd have delta E total equals what?
It would equal Q.
Equals Q for heat. Plus also possibly, what's another way you can transfer energy to a system?
Work, which is W.
Yeah, work. Heat and work are just two different ways of transferring energy. You transfer heat by doing what? What would cause heat to flow from one place to another? Like if I've got an object here and an object here, and I want heat to flow, what has to be true to allow heat to flow in the first place?
There has to be a temperature difference between the two objects.
Exactly. There's got to be some difference in temperature, a temperature gradient, a temperature difference. And heat is going to flow from the hotter object towards the colder object. If the objects are the same temperature, there's no heat flow. If they're at slightly different temperatures, you get a very slow heat flow. If they're at very different temperatures, you get a faster heat flow. So heat represents the transfer of energy caused by two objects or two locations being at different temperatures. Whereas work is a mechanical transfer of energy caused by pushing on an object. Anytime you got a force on an object that's moving, then work is being done. And that requires both force and motion. If I'm pushing on an object but it's not moving, I'm not doing work. If an object is moving but I'm not pushing on it, I'm not doing work. I'm only doing work if I'm pushing on an object in motion. In this case, there's no work being done because it's not like we're pushing on the ice or rubbing the ice to make it melt. We're just applying heat. So we can ignore work here and just say the change in E total is heat. And then we can expand delta E total by filling in all the types of energy that are changing. And if there were more objects, we'd include energy for each object. But in this case, there's just the ice. So this just splits out to delta E thermal for the ice and delta E bond for the ice. Any questions on that so far? And now we can fill in exactly those formulas we got earlier. MC delta T for delta E thermal. Delta M delta H for delta E bond. And there's not really any algebraic solving that needs to be done because we're trying to find the amount of heat, and heat is already isolated on one side. If it wasn't, if you were trying to find the value of a variable that wasn't already by itself, you'd want to isolate it algebraically and then plug in some numbers. And we have those numbers. The mass of the ice, for instance, is what?
Three kilograms?
Yeah, we've got 3 kilograms. And then specific heat of ice, we look up on a data table. So I've got a data table here. I'm just going to look up specific heat of ice. And I want kilojoules per kilogram Kelvin. That's 2.05. Kilojoules per kilogram Kelvin. And then how much is the temperature changing?
10 degrees, a positive change.
You can see that the temperature is increasing by 10 degrees. If it's not obvious from looking at the numbers, you can also just subtract final minus initial. Delta anything you can find as final minus initial. 0 minus negative 10 is positive 10. And since it's a change in temperature, Celsius and Kelvin are interchangeable. So I'm just going to write this as 10 Kelvin. And then for the bond energy, delta M, again, we could write this as final minus initial for the liquid. 3 kilograms minus 0 kilograms is positive 3. And how could I get the value of delta H?
You look it up?
Yeah, I could look that up on a data table again, because it's not like I'm the first person to ever want to know how much energy it takes to melt a block of ice. So again, I'm going to look up in the heat of melting column, look for ice 333.5. So 333.5 kilojoules per kilogram. By the way, if you've got time for it, it's a good idea to try memorizing the values for water, heat of melting, heat of vaporization, and specific heat, at least for ice and water, just because water shows up so frequently in situations like this. It's good to know those just as standard values without even having to look them up. And if we multiply and add all that up, that'll tell us exactly how much energy it takes to make this happen. So let's try that out. We've got, will liquid ice always have a mass? Oh, the 0 here is from the fact that we start with no liquid. Since we're talking about a transition between solid and liquid, you want to list the masses of the higher energy state. In this case, liquid is higher energy than solid. So we start with no liquid because it was all solid, and we end with 3 kilograms of liquid because we're melting all of it. So initial amount of liquid is no liquid at all. Final amount of liquid is 3 kilograms. Final minus initial would be +3. And if we multiply all that out, 3 times 2.05 times 10 plus 3 times 333.5, we get 1062. And yeah, the slope of the energy temperature graph is 1 over the heat capacity. So it looks like heat is 1062. And we want to be careful about units here. I would actually go through and check to make sure what cancels out. We've got kilograms in the numerator, kilograms in the denominator cancel out. Kelvins in the numerator, kelvins in the denominator cancel out. So this whole term is in kilojoules. Over here, we've got kilograms and kilograms cancel out. So this whole term is in kilojoules. It's a good idea to check that before adding them together, by the way. You can only add values together if they're the exact same units of measurement. In this case, everything's in kilojoules. So it takes 1062 kilojoules of energy in order to melt the whole block of ice. Any questions on that? Yeah, I would presume so. That on a quiz, I would presume it would be something like this information, and then you'd want to set all this up, figure out exactly how much heat it actually takes. And by the way, if you want some more general practice on stuff like this, I've got a few other practice problems on heat transfer and thermal energy and bond energy. If you go to math.andcheese.org/P7A, I'll put that in the chat. There should be a worksheet on thermal energy and bond energy if you want some more practice. Any other questions on that?
Could you repeat one more time how you got C in the final Q equals 2.05? How'd you get that number?
The 2.05, this was looked up on a data table.
Oh, okay,
on a data table, you just look, it's a data table listing specific heat of various materials, heat capacity, or not heat capacity, heat of melting, heat of vaporization, and temperatures of phase changes. So you would look that up on a data table, and under ice, it would list 2.05.
Okay, thank you.
And thermal energy and bond energy, I wouldn't say inversely proportional exactly, but it's certainly possible to have one increasing and one decreasing, yes. I don't have a file for the table of heat capacity, but you can look up most of them online if you just look up specific heat of ice or whatever on your favorite search engine. I'll see if I can put together, actually I do have some of them on that worksheet. If you click on the worksheet and scroll down, there should be a data table of the relevant information for those. I'll see if I can put together a more extensive one and put that online as well. All right, I'm gonna head out. Have a nice day, and I will see you on Thursday. You're welcome.